can be summarized as step number 1. First, assume suitable value of lambda. Assume lambda. What is lambda? That IC. Say IC equal to IC0. This is the first step. After that, step number 2, calculate various generations say PGIs. I is equal to 1, 2 up to number of generating units k. Using the equation equal incremental cost criterion, that is dCi upon d PGI is equal to 0, not 0, equal to lambda. This assume lambda. Say this is lambda 0. So right here lambda 0. How many equations? Corresponding to I is equal to 1, 2, k equations. One more thing, while calculating PGI, the various generations at different units, say I is equal to 1, 2, 3, PGI1, that is PG1, PG2, PG3 and PGK. If generation at a particular unit violates the limits, that is either greater than PGI max or lesser than PGI min, in that case we have to fix the generation at that particular violating unit at equal to limiting value. If lesser than PGI min, then PGI will be PGI min, or if more than PGI max, then PGI will be equal to PGI max. Then the remaining load of the load demand PD, that will be distributed among the remaining generating units. Third will be check whether all generations from all the units meet the demand or not. That is, check PGI I equal to unit number 1 to till unit number k, check if this minus PD is nearly equal to 0, say epsilon, where epsilon is tolerance, (10 to minus 6 minus 3, whatever you can tolerate, means the total generations is nearly equal to total demand, then stop iteration. Otherwise, step number 4, if generation is more, then decrease this assumed value of lambda. If generation is less, then increase assumed value of lambda, and go to step number 2. So next we can write, if generation is less than PD, or this minus this is less than 0, then increase lambda, or we can say else, if this is, that is total generation is greater than total system demand, then decrease lambda and go to step number 2 and go to step number 2 here, and this will be repeated unless we are getting total demand is equal to total generation, nearly equal to total generation. So, this way we will proceed for the iteration required for optimal load dispatch. Now, let us solve one problem on economic operating schedule. See, incremental fuel cost in rupees per megawatt hour for a plant consisting of two generating units of 100 megawatt each hour. This is ICs of the two generating units at a plant for unit 1 DC1 upon dPg1, that is IC1 is given by 0.012 Pg1 plus 2, and IC2 for second generating unit is given by dC2 upon dPg2 is equal to 0.015 Pg2 plus 1.5. Minimum load, that is PGI min, for on each unit is 10 megawatt. So, we can't load any unit below this, and total load to be supplied, that is demand PD, is equal to 150 megawatt. Determine the economic operating schedule. Solution for this is, first step will be assume suitable value of lambda. So, what do you mean by suitable value? It should be greater than the largest intercept of the ICs, the various ICs corresponding to various generating units. Suppose for 2 units, the intercept for unit 1 is 2 y intercept. This is equation of a straight line, something y equal to mx plus c, where this x is variable. Here the variables are Pg1 and Pg2, which are required to be determined. So, this assumed value of lambda should be greater than the largest intercepts of the various units. So, let us assume 3, obviously 3 is greater than the 2 intercepts. Corresponding to this assumed value of lambda, the various PGIs, that is Pg1 and Pg2, step number 2 of our procedure, will be Pg1. So, Pg1 will be nothing but this is now 3 lambda. So, this is 3, it means 3 minus 2 upon this 0.012, that will be Pg1. So, this is coming out to be 83.33 megawatt. Similarly, Pg2, equating this with assumed value of lambda 3. So, 3 minus 1.5 upon 0.015, that is coming out to be 100 megawatt. Now, check total generations whether equal to the demand or not. So, total generations is coming out to be more than the demand. It means we are generating more than the demand. So, decrease lambda. So, let it be lesser than 3, that is 2.7. Obviously, it should be greater than 2 at any cost. So, for this value of lambda 2.7, again using same equation, Pg1 will be 2.7 minus 2, this intercept, upon 0.012 equal to this one, and Pg2 will be 80 megawatt. This time the sum of total generations from the two generating units is coming out to be lesser than the demand, that is 150 megawatt. So, here it was greater than demand. For this value of lambda, it is lesser than demand. It means solution exists in between these, 2.7 giving more, 2.75 giving less. So, this time not, this was 2.7 giving less and 3 giving more. So, we will increase lambda. So, increase from 2.7, say it is 2.75. Now, for this value of lambda, which is increased from 2.7 to 2.75, again calculate Pg1 and Pg2. So, this time for this lambda is equal to 2.75, Pg1 is 62.5 megawatt and Pg2 is coming out to be 83.33 megawatt. Sum all the generations Pg1 plus Pg2, and this time again we see that it is lesser than, still lesser than PD. But we can note that we are approaching towards the load. Here we are far from the load, far from 150 megawatt, that is load. Now we have reached towards 150 load. So again we will increase lambda, but slight increment is required, otherwise we will have more than PD. So steps should be taken carefully. We know that our lambda should be less than 3 because corresponding to lambda 3 all generations Pg1 plus Pg2 is more than PD. So obviously it should be lesser than lambda 3, lambda is equal to 3, and more than lambda is equal to 2.75. So corresponding to 2.75 still it's giving lesser than that. So again increase lambda, this time it is 2.78. Corresponding to 2.78, Pg1 is coming out to be 65 megawatt and Pg2 is coming out to be 85.33 megawatt. This time the sum of all generations from the two generating units Pg1 plus Pg2 is coming out to be nearly equal, but still it is greater than PD. Suppose our tolerance is 0.1, so we can't tolerate this. So still we want to change lambda. This time lambda will be decreased because it is coming out to be greater than the demand. So decrease slightly. This is 2.78, that is 780. So take 2.778, slightly lesser than this. For this value of lambda, Pg1 is 64.83 megawatt and Pg2 is 85.2 megawatt. So Pg1 plus Pg2, that is 150.03 megawatt. Take difference, total generations minus demand. So this difference is coming out to be 0.03, that is within tolerance, pre-specified tolerance. Suppose we have specified our tolerance as 0.1. So 0.03 is lesser than 0.01. So now we have reached the optimal solution, and corresponding to this the loading on unit 1 is Pg1, that is 64.83 megawatt, and loading on generating unit 2, that is Pg2 is 85.2 megawatt. So this way it's something like heat and trial. We have to tune lambda. Corresponding to that we will get different combinations of generations from the various generating units. You can practice for more than 2 generating units. So far we have discussed the economic operating schedule without considering transmission losses. So when transmission losses are considered, then the procedure will be different. Suppose this time we are considering transmission losses also. So right here optimum load dispatch considering transmission losses. Suppose we are having 2 units, unit 1 and unit 2. Say this is unit 1, this is unit 2. This is line in between these 2 units, R plus Jx, and load is connected near to unit 1. These 2 units are identical. It means the incremental cost curve of the 2 units is same. So for any load, using simple equal incremental cost criterion, we can conclude that the load should be divided equally. As load is near to unit 1, unit 2 has to supply the additional loss occurring through the line apart from the load while supplying the load. So it is more economical to load unit 1 more and more than unit 2, although the IC curve of the two units are identical, but it will be more economical to load more and more unit 1 than unit 2 for any load, because this time we are considering transmission losses also. So while considering transmission losses, the simple equal incremental cost criterion is no longer valid. So we have to consider this effect also. This time our optimization problem, which we have discussed in previous lecture, minimize. Our function is C, total cost, that is cost of ith unit, which is function of PGI. I is equal to 1 to k. Suppose this time we are having k plants, and Ci is the cost of ith plant while generating PGI. Suppose plant number 1, I is equal to 1, so cost will be C1, that is function of PG1. PG1 is the generation at first plant. So for I is equal to 2, we will get C2, function of PG2. PG2 is generation from the second plant, and so on up to kth plant. We may write total cost is this, and our objective is to minimize this cost. Subject to now constraints, subject to the same constraint, power balance equation, but this time we have to consider the system loss also. So right here constraint should be total generations, minus demand minus PD, demand is PD, minus PL should be equal to 0. Let us denote it by equation A. This is power balance equation. So this time we can observe this additional term PL. What is PL? PL is the total transmission loss. PD is total demand, and PGI total generation from the K plants. Now again we will use Lagrange function for optimization, because it is multi-variable optimization problem. Variables are PG1, PG2, PGK. So number of variables are here K variables, PG1, PG2, PG3, so on, PGK. So it is multi-variable optimization function with equality constraint. So such problem can be solved using Lagrange function. So let us make Lagrange function L as this function, that is k equal to 1 to k, this is I is equal to 1 to k, Ci Pgi minus or plus Lagrange multiplier. We are having only one constraint, so let us introduce lambda 1 or lambda, minus or plus we may write, times this constraint. So this is I is equal to 1 to k Pgi minus PD minus PL is equal to 0. This is our Lagrange function. So necessary and sufficient condition for optimal solution, we may write del L upon this L upon del PGI is equal to 0. This is necessary condition. This implies del Ci upon del Pgi, because this is C1, C2, C3, so only Ci will depend on Pgi, because we are differentiating with respect to PGI. So say I is equal to 2. So this will be C1 function of PG1, C2 function of PG2. That will depend on PG2 only. Other terms C1, C3, C4 like that will be independent of PG2. So we will get only dCi, del Ci upon del PGI, or we may write dCi. Why? Because Ci is depending only on PGI. So we may write this minus lambda is constant, take here, and this is nothing but PG1, PG2, PG3 again 1, we will get 1 minus, because other terms independent of I, that is suppose for I is equal to 2, this will be PG1, PG2. So differentiating this with respect to PG2 will give 1 only corresponding to PG2. PG1 will give 0, PG3, PG4, PGK will give 0, so 1 only. This is constant 0 minus. What about PL? PL is not independent of PGI. PL is total losses in the system. So total losses, transmission losses in the system will fully depend on PGIs, PG1, PG2 up to PGK, the various generations from the various plants, at the various plants. So under certain approximations, we can assume that this PL is only depending on PGI. What are those assumptions? Let us assume the power factor at each bus is remaining constant, is constant. So in that case, PL is only depending on PGI. So right here del PL upon del PGI is equal to 0. This may further be written, can be written as dPGI, this, send it this side, is equal to lambda times 1 minus del PL upon del PGI. Or this can further be written as dCi upon dPGI upon, you may write upon 1 minus del PL upon del PGI is equal to lambda, or dCi upon dPGI times Li is equal to lambda. Let us denote it by equation D, where L is, can be written as 1 upon 1 minus del PL upon del PGI. This is known as penalty factor at ith plant. So Li, penalty factor, can further be written as 1 upon 1 minus, this is incremental transmission loss at ith plant. So we may write ITLI. What is ITLI? Incremental transmission loss at ith plant, that is del PL upon del PGI, or Li, penalty factor. What is dCi upon dPGI? Incremental fuel cost at receiving end of ith plant, corresponding to ith plant, but here we are considering the transmission losses also. So this way we have how many equations? Here I is equal to 1, 2 up to k. So corresponding to different values of I, we are having different equations. So how many equations here? K equations. And how many equation here? One equation, power balance equation. So total we are having K plus 1 equations. And how many unknowns? Pg1, Pg2, Pgk, K unknown here and one unknown, addition unknown lambda. So K unknowns, K equations are enough to solve the problem, right? So this coordination equation, where lambda, what is lambda? Lambda is the incremental cost of received power in rupees per megawatt hour. We may write lambda is equal to incremental cost of received power in rupees per megawatt hour. Li is penalty factor of ith plant and dCi upon dPgi is incremental fuel cost of ith plant. As we have discussed that total loss PL, this PL depends on PGIs, PG1, PG2 dot 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 PGK are done under certain assumptions. Suppose the power factor at all buses are constant. So several ways are available to express these losses and their dependencies on the power generations. One of this is B coefficients. So right here the dependencies of PL on PGIs using B coefficients. B coefficients method is simple but approximate. So that can be expressed as PL is equal to, say, M or I, whatever, right here. M is equal to 1 to K, where K is number of generating plants, N is equal to 1 to K, PGM, BMN, PGN, where PGM is generation at mth plant. In general, we can say PGI is generation at ith plant. Similarly, PGN is generation at nth plant. What is BMN? BMN is equal to BNM. B12 is equal to B21 or so on, is loss coefficients. Loss coefficients which is constant under certain assumptions. Certain assumptions. So the order of this m is equal to 1 to k, n is equal to 1 to k, or first write in matrix form. So in matrix form, the same can be represented as PG transpose B PG, where PG is equal to PG is equal to PG1, PG2, PGK. Let us write for 3 plant system. Suppose there are 3 plants only, K is equal to 3. Corresponding to that, this can be written as, what about B? B is nothing but B11, B12, B1K, B21, B22, B2K, this is D, B1K, bk1, bk2, bkk. So order of this matrix is k cross k. This is order k cross k. So suppose for 3 plant system k will be 3. So the order of this matrix will be 3 by 3, and this will be Pg will be Pg1, Pg2, Pg3. Let us write here for 3 plant system Pg is Pg1, Pg2, Pg3, right, and B will be B11, B12, B13, B21, B22, B23, B31, B32, B33. So total 9 coefficients. What will be 3 by 3. So write PL. So PL will be PGT right here. PL will be PGT, that is Pg1, Pg2, Pg3, and this B here, B11, B12, B13, B21, B22, B23, B31, B32, B33 times Pg. So Pg is Pg1, Pg2, Pg3. Solve it. So this is nothing but equal to Pg1, Pg2, Pg3. This one, multiply this with this. So we may write this with this. So B11 Pg1, B12 Pg2, B13 Pg3. Right here, B11 Pg1 plus B11 Pg1 plus B12 Pg2 plus B13 Pg3, B13 Pg3. So next multiply this and put here B21 Pg2, B21 Pg1 plus B22 Pg2 plus B23 Pg3. The last row corresponding to this. So B31 Pg1 plus B32 Pg2 right here. B31 Pg1 plus B32 Pg2 plus B33 Pg3. So multiply this again with this right here. The next line, this is PL. So this PL may be written as is equal to so multiply this with this. So Pg1 will be multiplied with this. So this will be B11 Pg1 square. PL will be B11 Pg1 square. Again B12 Pg1 Pg2 plus B12 Pg1 Pg2 plus B13 Pg1 Pg3 B13 Pg1 Pg3, right. Next we have multiplied this with this plus. So multiply Pg2 with this second row. So this will be B21 Pg1 Pg2, this with this, plus B22 Pg2 square Pg2 square plus multiply with this B23 Pg2 Pg3 B23 Pg2 Pg3 plus multiply Pg3 with the last row of this. So B31 Pg1 Pg3 plus B32 Pg2 Pg3 plus B33 Pg3 square B33 Pg3 square. So this implies the total transmission loss can be written as, take square terms initially, B11 Pg1 square plus this is written, second square term is here, B22 Pg2 square plus this square term B33 Pg3 square. Plus B12. Remember B12 is same as B21. So B12 is here, B21 is here, and Pg1, Pg2 is here, the same Pg1, Pg2 is here. Directly we can write twice of B12, Pg1, Pg2. So right here twice of B12, Pg1, Pg2 plus B13. Search for B31 here. So we may write twice of B13 Pg1 Pg3. Next is B23 plus B23 is same as B32, this one. So we may write twice of B23 Pg2 Pg3. So this way we can express the total transmission loss using V coefficients for any number of plants. Presently we have considered 3 plant system, so that can be extended for any number of plants. Now let us calculate del PL upon del PGI, because now we have expressed PL in terms of V coefficients. So del PL upon del PGI, incremental transmission loss del PL upon del PGI at ith plant. Incremental transmission loss at ith plant can be written as del upon del PGI. So for K plant system we have M is equal to 1 to K summation sign, N is equal to 1 to K PGM BMN PGN. So PL can be written as this one, we have already discussed it. So we have to take partial derivative of this PL with respect to PGI. So the terms independent of PGI will be 0, and the terms depending on PGI will give non-zero values. So first let us discuss on the number of terms. The number of terms will be m is equal to 1 to k times n is equal to 1 to k. So total number of terms will be k square, right here somewhere, total number of terms k square. So total number of terms independent of PGI, or write one more step, this will be del upon del PGI. Remove m is equal to I and n is equal to I, that will give PGI. So remove that, so that the term independent of PGI can be written together. Right here, m is equal to 1 to k, m is not equal to I, and n is equal to 1 to k, n is not equal to I. PGM, BMN, PGM. So we have removed ith term from both the summation sign. So this whole will be independent of PGI. How many terms? So m from 1 to k except I, so k minus 1. N is equal to 1 to k except I, so k minus 1. So total number of terms will be k minus 1 into k minus 1, that is k minus 1 square. So this is equal to k square, total number of terms, this is equal to k square minus 2k plus 1. So subtract this from this. So total number of terms which depends on PGI corresponding to either m is equal to I or n is equal to I, or both m is equal to I or n is equal to I. At least one PGI will be there, hence depending on PGI. So we can subtract total number of terms k square minus terms independent of PGI. So this will be minus 2k minus 1, where k is number of plants. So total number of terms depending on PGI is 2k minus 1. So write the next term. Next term will be, take ith, m is equal to I here, others we have considered. So m is equal to I will give PGI, BIN, PGN. So right here corresponding to m is equal to I, summation this whole, n is equal to 1 to k, n is equal to not equal to I, m is equal to I, hence write PGI, BIN, put m is equal to I everywhere, PGN, plus this time take I here from here, n is equal to I. So this will be m is equal to 1 to k, m is not equal to I. This time substitute n is equal to I. So this will be PGM, BMI, n is equal to I, PGI, plus when both are equal to I, m is equal to I, n is equal to I, this time this will be PGI, m is I, n is I, so BII, PGI, n is equal to I. Let us cross check the numbers. So these terms are k minus 1 whole square. So remaining terms should be difference of k square minus k minus 1 whole square, that is 2k minus 1. So number of terms here is n is equal to 1 to k except I, k minus 1. Here also k minus 1. So 2k minus 2 plus 1, 2k minus 1. Hence the total number of terms depending on PGI, in which at least one PGI is there. One PGI is here, others are constant with respect to PGI. One PGI is here, so others are independent of PGI, these two terms except PGI. And here we are having PGI into PGI depending on PGI. So next we can write, this can further be written as incremental transmission loss at ith plant can be written as del upon del PGI, this one. So this is constant independent of PGI, hence write 0 corresponding to this plus corresponding to this, only PGI is depending on this. So this will be summation n is equal to 1 to k, n is not equal to I, bin pgn, bin pgn plus PGI is here. So right here m is equal to 1 to k, m is not equal to I, this is PGM BMI plus PGI into PGI, PGI square, so twice of BII PGI. This can further be written as, here n is equal to 1 to k, n is equal to not I, m is equal to 1 to k, m is not equal to I, or put m or n j. So these two are basically same except ith term. So ith term can be written as, one can be sent here, one can be sent here. So this can further be written as, directly we can write this is equal to, let us denote it by j, j is equal to 1 to k, bij and bij here also. For this also we will represent by j is equal to 1 to k, so twice of that, and two terms are here, so ith terms are also here and there. So we can write twice bij, because bin is equal to bni, b1 to b21 are same, bij pgj. So del PL upon del PGI, incremental transmission loss at ith plant can be written as this, where I is equal to 1 to k. Incremental fuel cost. So let us assume that the polynomial corresponding to the cost curve of ith plant is represented by Ci is equal to half the same representation Ai Pgi square plus Bi Pgi plus Di. Let us represent Di. So incremental fuel cost can be written as dCi upon dPgi is equal to Ai Pgi plus Di. This. Substitute these values in coordination equation. We can substitute here itself. So we may write dCi upon dPgi, that is Ai Pgi plus Bi is equal to, that is dCi upon dPgi is equal to lambda 1 minus del PL upon del PGI. So del PL upon del PGI is j is equal to 1 to k summation j is equal to 1 to k 2 bij PGJ. So this can further be written as, we may rub this, or better rub this whole. So this can further be written as Ai Pgi plus Bi. Take this one this side. So this minus will come plus lambda j is equal to 1 to k 2 bij pgj 2 bij pgj is equal to lambda. We want to express pgi in other terms, in terms of the other variables and parameters. So, separate the ith term pgi. So, we may write ai pgi plus bi, take ith term. So, we can write lambda, ith term will be times 2 bii, because j is equal to I will give bii pgi plus lambda, write this except ith term, j is equal to 1 to k, j is not equal to I, because ith term we have taken here, 2b ij pgj is equal to lambda. Take pgi together, this implies ai, we have taken this, plus 2 lambda bii times pgi, we have taken these two terms, set the other terms independent of pgi on right hand side, is equal to lambda is there minus bi, this term. So, remaining terms are this minus lambda, j is equal to 1 to k, j is not equal to I, 2b ij pg. So, take pgi one side, or we may write here, this implies pgi is equal to this pgi is equal to this upon this. So, this is lambda I minus bi minus lambda j is equal to 1 to k, j is not equal to I, 2 bij pgj. Upon this ai plus 2 lambda bii. Divide, this is lambda, not lambda I. Divide numerator and denominator by lambda. So, this can further be written as or directly we can write here itself. So, lambda upon lambda, this will be 1 minus bi upon lambda, this lambda is gone because we are dividing by lambda, upon ai upon lambda plus 2 bii plus twice of bii, rightly write here, ai upon lambda plus twice bii. So, our coordination equation represented by equation B can be written by say equation C. Let us name it equation C. So, equation B and equation C are same. Here we have represented total transmission loss using B coefficients. So, this equation, this is coordination equation same as equation B, is solved iteratively. So, this way This equation C is solved iteratively for all PGIs. I is equal to 1 to k. We may write where I is equal to 1 to k. So this time two iterations will be run. One iteration will be for corresponding to PGI only. So initially assume any value of PGI for a particular value of lambda. For a particular value of lambda, assume any value of PGI. Simple way is solve the simple incremental cost criterion condition. Equal incremental cost criterion condition can be used to get or to guess initial values of PGI, and iterations will be started and PGI will be calculated. At each iteration, we will check the corresponding changes in PGI in previous iteration and next iteration. If there is no further change in PGI, that is the difference of PGI in present iteration and previous iteration is within tolerance, we can stop, we can take that those PGI, or we may write the various steps. So here also step number 1 will be assume suitable value of lambda. Step number 1 for solving economic dispatch problem considering transmission loss, we write our steps as assume suitable value of lambda. This time also this lambda should be greater than the largest intercept of the IC curves of the various plants, that is BI. Here right, BI, so B1, B2, B3, it should be greater than the largest value of BI. Next, after assuming this, assume initial values of PGIs first, because here PGJs are, or may write assume or calculate values of PGJ using simple equal incremental cost criterion. Corresponding to this lambda, you may write dCi upon dPGI is equal to lambda. Corresponding to that, you will get PGJ. So calculate PGIs or PGJs using simple equal incremental cost criterion. Third, solve equation C for PGI. Suppose you want to solve for PG1. So the values of PGJ except PG1, here j is not equal to I. So here we need to write PG2, PG3, PG4 like that. Those PGs will come from step number 2, which has been obtained using simple equal incremental cost criterion. So solve equation C for PGIs. We can write PGIs. I is equal to 1, 2, 3, 4, 5. Iteratively, which we have already discussed. So once iterations are obtained, solution is converged corresponding to PGI, these iterations are stopped, we will sum up all PGIs. So next step we may write sum of all PGIs, that is PGI I is equal to 1 to k. This should be equal to, this time we are considering transmission loss also. So this should be equal to demand plus loss. So minus PDI minus PL, total generations minus total demand minus total system transmission loss. Ideally should be equal to 0 or same. If this is less than tolerance, any tolerance which we can tolerate, right here tolerance, then stop iteration. Which iteration? This primary iteration, which for this iteration our first step is assume suitable value of lambda, then calculate this, then solve this. Here second iteration is there. So after this iteration, once solution corresponding for PGI is converse. We are using those PGIs here and we are comparing with this sum of load and demand, demand and loss. So if it is within tolerance, some pre-specified value, so a stop iteration, this primary iteration, a stop iteration, if we may write here, if this is this, then a stop iteration. Otherwise, else, next, else if, okay, we don't have calculated PL. So we are required to calculate PL also before comparison. So this will be a step number 5, we may write, this is a step number 5, and before that a step number 4 will be, I am writing here. So a step number 4 will be calculate PL, and PL is nothing but using B coefficients. We have discussed m is equal to 1 to k, n is equal to 1 to k, PGM, BMN, PGN. So calculate PL. Once PL is calculated, PD is known, total demand. So compare this. If this is within tolerance, a stop iterations, else or otherwise, if generation, total generation, that is PGI, summation I is equal to 1 to k minus PD minus PL is less than 0. It means total generation is less than the demand plus loss, system loss, then increase lambda, then increase lambda, or if total generation PGJ minus PD minus PL is greater than 0. Either total generation is less than the demand plus loss or total generation is greater than the demand plus loss. In that case, then decrease lambda and go to step number 2. So lambda is modified here. If this is not fulfilled, then lambda will be changed according to this check. So check number 1, if total generation is less than the demand plus loss, so lambda will be increased. If total generation is greater than the demand plus loss, then lambda will be decreased. This lambda, initial assumed value of lambda will be decreased, and go to step number 2 unless this is satisfied. So once the iterations are stopped, means this condition is satisfied. So this will be our solution. PG1, PG2, PG3 corresponding to this condition will be our solution, means optimal loading at various plants. This way we can solve the economic dispatch problem. Thank you very much.